So this video is going to help with section 9.1. And what we're doing is we're really starting the chapters that you're going to be tested over. And we're starting this idea of limits and kind of starting to look at some of the calculus concepts. So when we look, sorry, it's a slight bit blurry, but that's just kind of the way it showed up on here. So when we look at what is a limit and what am I talking about? The idea is really where are you headed at a certain X value? Okay, so where are you going? What is the Y value? So a lot of what we're looking at is what is the Y when you're at a specific X on a graph, but a little bit more detailed than that. So I have this first graph here, and they're like, here's X equals 2. And they want you to look at right before and right after. Like, where are you going as you get closer and closer to 2? So if we go up at the actual 2 value, we're here at 4, right? But it wants you to see both sides are going to 4 as you get closer and closer. So we'll look at the left side, which is coming from the negative, and we'll look at the right side that is coming from the positive. And where are they headed? So we don't just say, oh, well, at 2, you're at 4. We don't just, it's not that easy. Some of them are, but we want to look at the left and right side. So some of your homework will be literally looking at the left and from the right. Some will just say, what's the limit of this? Okay, and here's the value right here, or the function, excuse me. So you can easily go, well, 2 plus 2 is 4. So yes, at 2, you're at 4. Okay, so this is symbolically what the limit looks like. The limit as x approaches 2 of the function given is 4. This could also be written as the limit as x approaches 2 of the actual function here in parentheses, like that. That looks like ln, but it's a limit. Okay, so as x approaches 2, we could put the 2 value in and see it's going to go to 4. Why do we care? It's like, just put the 2 value in. Well, some of them aren't this pretty. Okay. So we start to talk about breaks in the graph and holes in the graph. So let's scroll down and look at example 2. Hopefully you can see this, but this is a round and a solid, and an open and a solid, like this. So when we're looking at this, now we're saying, well, what happens if you're getting close to 1? Okay, so as we get close to 1, it's written here in linear or in limit function. But where is it going as we get close to 1? Well, the left side is headed to 3 and the right side is headed to 3, even though the value at 1 doesn't actually exist. The limit still exists because the left and the right side are both going to 3. So we don't have a value at 3, but we do have a limit at 3 because the left side is going to 3 and the right side's going to 3. Okay, as we get closer right in here, right in here. All right, which is different. Typically, if we were looking at a function at that value, we'd say undefined. Whereas this, we're not saying undefined. We're saying it has a limit. Both sides are headed to 3. Okay, then one other thing we got to point out, though, is the value at 1 is not defined. There is no value at 1, but the limit exists and it's going to 3. Okay, so what if we are looking at that same graph, but we want to see -1? So as we get closer and closer to -1, well, look here. Here's -1. We get a dot, dot, dot. Here's our -1. So I can see that left side and that right side are going to the value 1, right? So they're both headed to 1. So we could say the limit of that function and the value of that function are both 1. They wrote them together. I don't love that. I would like them separate. Like the limit is going to 1 at -1, right? And the value at -1 is 1 also. So like the other one had an undefined value, but this one has both. Okay. And that's what it's trying to show you here is you're getting closer and closer and closer. So it's going to be at that 1 right here. I like the little lines getting closer and closer, kind of show you that. Okay, my last one is what about at the value 2? So notice at 2, right? There's a solid dot here and an open dot here. So the value is here. So if I put in 2 to the actual function, then I would get 2 out. But what about the limit? Well, look at the limit. See how they have a negative right here and a positive? What they're saying is left side, right side. Okay, so this is the notation for left, and this is the notation for right. So this is left side. This is right side. Because we got to be able to say, because they're different on this one. Let me do the left side. I'll just do that in red. So as I get closer and closer here to this solid dot, right? I'm getting closer and closer to 2, which is what they have here. They say you're getting closer and closer to 2. Great. But on the right side, as I come in closer and closer to 2, and it's an open dot, but as I get closer and closer, I'm all the way up at 5. So this, you're coming in from this way to 5, and you're coming in at this one at 2. So there is no limit because they are not going to the same value. Okay. So we don't care so much what the value is at that yet, but we can see left and right side, they have to be the same. You can't have a broken graph at the spot you're looking at. That's the kicker, right? No broken graph. You can have a hole like we did in the other problem, but you cannot have a broken graph. So what we would say here is we would say the limit doesn't exist at 2, but the value does. The value is at 2. It does have a value because it has a solid dot at 2. Okay, so that's kind of graphically that idea. Now we're going to start looking at some of these just from the function, so it gets to be a little bit trickier. You can always graph them and look at the graph, always. You can also always look at the left and right and make sure they're going to the same value. That's a skill you really want to use. If you're stuck on something, look at the left side, look at the right side, see if they're the same number. Okay, indeterminate form, I'm going to skip for just a couple minutes and then we'll come back to that idea. We're going to skip all this fancy properties for now. Let's just look at a couple problems. So here's our problem. We don't have the graph. We're just like, okay, x is going to 2 at the function 9x plus 5. So what you just start with is you just put that value in. So I would go 9 times 2 plus 5. So 9 times 2 is 18. And so what is that, 23? So where is this headed? It's headed to 23. And it's headed to both sides. This is a linear line, right? So we're fine with just putting that value in. So you could graph this and look at that graph to see it's a line. But really, we just put that value in. If it had a hole, it would need, or break in its graph, it would need to have a step function of some sort, right, in order to have a break in your graph. So these kind of functions we're looking at up here, they don't have a break in the graph necessarily yet. At least 1 and 2 and 3 don't. Okay, problem 2. What am I going to do with that 3 value? Oh, excuse me, -3. I'm just going to put it in. What is 5 times -3? -15. So the limit is going to -15 at -3. Okay, so you can see how this is really finding your y values, right? Like what's happening at that y. So 5, we would have 2 places for 5, and then you'd have 5 times 5 plus 7. So 25 plus 7 is 32 inside. So what is 5 times 32? I don't know. I'm going to use my calculator. I get 160. Still, I'm able to put the value in, works out great. Problem 4 starts to be a little different. You could have a hole in your graph when you have asymptotes, right? When you have values that don't work. So this one does work because we're not putting in -2. That makes 0 in the denominator. So I'm putting in -1. So I would still have -1 plus 8 on the top, -1 plus 2 on the bottom. So that's going to give me 7 over 1, or just 7. So that one was pretty. If I was putting in -2, I would have gotten a number over 0, which is undefined. So you don't necessarily have limits. Well, you have to be careful of where there's an asymptote. You really need to look at the left and the right sides separately. We're going to do some of those, so we'll get to the harder ones. So 5, we can't have a negative under the radical. We'll see what happens. We're going to have -8 times -3 plus 1. So -8 and -3 multiplied to +14 plus 1's 25. So we're going to have the square root of 25, which is just 5. Sweet. All right, so just 5. So it came out pretty. If it was a negative under the radical, then we'd have to look at some more things. Okay. Now, they have some rules that we kind of skipped over here. Basically, these rules are saying, like, um, if you just have a horizontal or vertical line where it's a constant, and that wouldn't be a vertical, but a horizontal line where it's a constant number, then it doesn't matter what value you put in, that would be the answer. So if I have, the limit of some number, it doesn't matter what I put in, it's just going to that number. So if it's horizontal at 2, any value I put in, it's going to be a 2. So that's what that's trying to tell you here. Okay. Then we have some kind of cool rules that say if you have two separate functions being added, you could actually take the limits separately and add them. Same with subtraction. Same with something being multiplied out front. You could just kind of keep that number, find the limit, and then multiply them together. Okay. With multiplication, you could break it up also. You could also break up, this is super helpful. This just makes a lot of these a lot easier. You can also break up a fraction as long as there's not a 0 in the denominator. Okay. And you can also, it's kind of, this one we don't really use that much, but you could also look at the whole square root of the value that you get. It's kind of what that's trying to tell you. So that helps with this, just these couple problems. We won't see a lot of these, but they're just kind of to help you think through what's allowed in those properties. So if I know the limit as x goes to 3 of x goes to 3 of 7, so times the function. Okay, so this is an f function here. We know that this equals 5. So basically, ignore the 7. This part equals 5. And we are already told if we have a constant, we can multiply it by the answer. So what it's trying to say is you can take that 7 and move it out front of this function here. And then you could replace that function with that 5. So that would give you 7 times 5 because they gave us that answer. They have to give me that. But basically, you can take a value out and just times it. So 7 times 5 is 35. And that's your answer. So I know that seems a little tricky, and a lot of people get stopped up on these, and I don't really want you to spend a ton of time on them. They're really not our main idea, but they are properties that are allowed. Okay, so problem 7 is 2 of those, so 3 and 2, and you're subtracting. So I can look at these separate and think 3 times the function f has a 5 value minus the 2 times the function g had a -4 value. So all I did was, I know it's going to 3, going to 3, going to 3. That's important. So I keep the 3, keep the 2. This value was 5, this value was -4. And then I just simplify that. So 3 times 5 is 15. So 15, -2 and -4 is going to give a +8. So just 15 plus 8 is a 23. Okay, same idea for 8, right? We're gonna have to do 2 on the top and bottom, so it's 2 times the 5 on the top and 3 times the -4. As long as we don't make a 0 in the denominator, we're safe. So I'm gonna have 10 over -12. Okay, so then we start to look at, some graphs that are going to have a break, right? So we know the limit may not exist or it might. So we have to look a little bit more specific. So this one says to use this top function if your value is less than 1, and this one if greater than 1 or equal to 1. So we are at 1 from the left side. So we're getting to 1 on that left side. So just think of a number line, right? Here's the value 0, so here's 1. If I'm coming in from the left side, right, then those numbers are less than 1. So I'm going to use the top function. And I would need to do, if I'm doing the left side, I could put 1 in there, but that is where you're equal. So you could do this is our first time looking at this. What I can do is numbers that are getting close to that value. I'm going to do it this way, y, and then I'm going to put my function in the middle, and that's x to the third plus 3. This is an h table. Instead of just x, y, I show my work. That's it. So what is something really close to 1 would be like 0.9. You're like just a little bit lower, right? Is 0.9. So then I'm going to take 0.9 to the third plus 3. So zero point 0.9, oops, not negative, zero point 0.9 to the third uh, plus 3. I get 3.729. Okay. And then let's go even closer, which would be 0.99. So I'm getting really close from the left side. So 0.99 to the third, and then plus 3. I get 3.9703 around there. And that was 0.99 to the third plus 3. Okay, if we want to even get closer, can you see that it's going to 4? Yeah, it's headed to 4. I can see it's getting closer and closer. So I could put in 0.999 and see, it's even going to be closer, right? So 0.999 to the third plus 3 is 3.997. So we can see it's getting really close to 4. What's another way that we can check that that's getting to 4? We can graph it. So I'm going to show that real fast. I'm going to use Desmos because it's so much easier on the iPad just to open Desmos. So we need x to the third plus 3. I'll move that over so we can kind of look at it. And we're looking at the value of 1 from the left side. I can't point to it because it's in Desmos. I can kind of tap at 0, we're at 3, and you can kind of see 1 over is right here, right? You can see I'm trying to get to 1. Ooh, did you see the 1, 4? But right before, we're just a little before, we're headed to 4. So we can see on the graph, it doesn't have a break. It's pretty. But at 1, we're switching to the other function. So this is all headed to 4. Okay, so let's look from the positive side. Now we have to use the bottom function, and we're going to be coming from the other direction. So as I pick values to get closer and closer of this function, then we got to get close the other way. So like 1.1, right? Because we're just a little bit above. So I'm going to put 1.1. So 3 times 1.1 plus 1. I got 4.3. And then a little closer would be 1.01. So we're using 0.1, 0.01, 0.001 on one side and the 0.99s on the other side. Now it could be, 2.1, 2.01, 3.1. It could be 3.99. You just whatever you're getting close to. Okay, so 1.01 times 3 plus 1 is 4 point. It's just going to move your decimal over 1. 4.03. And this is 3 times 1.01 plus 1. If we kept going 0.0001, right, closer and closer, we're going to see that this is headed to 4 also. So let's bring that graph in. So we have two graphs, though. We have the graph 3x plus 1, and we can see that I don't remember how to make this go from a number to a number. I don't think I remember how to do that. No. So we can see up until the value 1 right here that I just touched, the 1, 4, we look at the red, and then above we look at the blue. So they're both going to 4 at that value. Okay, so if we go back to full screen, then we can say because the left and right side are the same, there is a limit. It is at 4. But we had potential. Those graphs start at the same point. What if one started way over here? Then they would have had a break. There would not have been a limit. Okay. What is the value of 1? Well, we put that just into our function. That's what you've been doing for a long time. I put that into the bottom function, and I get 3 times 1 is 3 plus 1 is 4. And these don't all match necessarily. They do on this one. Okay. Um, all right, I'm going to go ahead and make this part 1, and then I have to go teach, then I'll make a part 2.